everyone and welcome to another webinar of Würth Elektronik ISOs. My name is Son and I will moderate this webinar today. Our topic of the day is understanding and selecting capacitors, fundamentals, technologies and latest trends. Our speaker today is Lukas Hölscher. Lukas, hi.
Hi.
Cool to have you here. He will hold the presentation and after that he will answer your question. So now we will start with the presentation. I wish you an exciting webinar and see you in the Q&A session.
Yeah, hello to all of you. Warm welcome from my side. My name is Lukas Hölscher. I'm Field Product Engineer at Würth Electronics. I've been working for 8 years in the product management for capacitors. And today we will speak about some basics of capacitors. I will show you a general overview and we will speak about some special features of each capacitors and some special applications. So first of all, we will start with some technical basics and an overview, and then we will go through the different technologies such as MLCC or film capacitors or even aluminum capacitors. And also aluminum capacitors in today's seminar, they consist of electrolytic, aluminum polymer and aluminum hybrid polymer capacitors. And then we will also have a short view on the DC link application. And afterwards we will do a summary of the seminar, and finally I'm very happy to answer your questions which might come up during this webinar. So first of all, let's speak a little bit about the general construction of a capacitor. You see here the construction of a parallel plate capacitor. In order to calculate the capacitance, you can use the permittivity and multiply it with the surface and divide it by the distance. So therefore, to increase the capacitance, you can either increase the area or decrease the distance between the plates. If you cannot change it due to several reasons, you can use a different material, such as selecting another epsilon r. And you see here on the right-hand side the epsilon r of different technologies. So for example, if we speak about vacuum, the epsilon r is a factor of 1. But if we compare it with polypropylene, for example, you see the factor is 2.5. We use polypropylene especially for our film capacitors. So you can see that you can get more capacitance with polypropylene if you compare it, for example, to vacuum or to air. And if we also have a look at some other technologies such as aluminum oxide, which will be used for aluminum electrolytic capacitors, for example, or even aluminum polymer, the factor is 9.3, which means that you can get way more capacitance in the same package with aluminum electrolytic capacitors in comparison to film capacitors, which consist of polypropylene, for example. So therefore, there is some technical difference already in behind, which explains the different capacitance of these values, of these technologies. So, but a capacitor is not only a capacitor, which you can see here. This is the capacitor of the capacitor. So. Or the capacitance, which gives us the benefit. It can be charged and it can be also used as energy storage. But we have also, for sure, we have some losses, which is described with the ESR. So the ESR mainly is the main reason why we have some heating inside of the capacitor, and this can also limit the lifetime. Then, for sure, we have also always some inductance, which is especially important in the high-frequency behavior of this capacitor. And then, for sure, for capacitors, we always have the insulation resistance or leakage resistance, which means, the smaller the insulation resistance is, the higher the leakage current is. So therefore, the insulation resistance should be as big as possible, for sure. So if we combine all these different effects, we see here on the right-hand side the frequency curve. We can see here the capacitance. Then we can also see the inductance, or the XL in this case. And then we can also see the ESR. And if we sum everything up during the calculation, then we see the Z, which is the total impedance. And you can also see the resonance frequency is the point where we have the lowest impedance. And there you can also see the ESR of these, there you can also see the ESR. So this is basically some information about the parasitics of capacitors. So there are different capacitor types on the market, such as if we, you can also have the fixed capacitors, or capacitors with a fixed capacitance, and also capacitors with a variable capacitance. So we will mainly focus on the fixed capacitors, because variable capacitors, it's not our focus at the moment. So therefore, we will discuss today or speak today about the ones with fixed capacitance. For example, the film capacitors, you can see here the paper film capacitors and the plastic film capacitors. We cover here the plastic film capacitors. Then we have the ceramic capacitors with class 1 or class 2 ceramics. Then we have also the electrolytic capacitors, which consist of aluminum electrolytic capacitors or tantalum capacitors, for example, or even niobium capacitors. So you can also see that the aluminum electrolytic capacitors are shown here, and here are also the aluminum polymer and aluminum hybrid polymer capacitors in behind. Maybe some words regarding tantalum capacitors. For sure, they have big benefits because they offer a lot of capacitance in a fairly small package, but they have some disadvantages that, for example, they can catch fire if not operated properly. So this was one of the reasons why we decided to not cover these parts in our portfolio. Then we have also the supercapacitors. We have EDICs, so electric double layer capacitors, and you have also pseudocapacitors or hybrid capacitors, but the basic function is more or less the same, so a lot of capacitance and fairly low voltage. And then there are also mica capacitors, glass capacitors, feed-through capacitors, but these are capacitors with fairly small usage, but for some applications they also might be interesting. So if you want to select a capacitor, I think then it's always interesting, okay, for which technology I have to look, or which technology can I use. So we have here an overview with the voltage and the capacitance, and you can see that by far the biggest area is here MLCC. So they cover the biggest range here. But even if you have a look at the high capacitance values, we have to speak about this later on. So the capacitance might change due to some other effects, applied voltage, for example. If we have a look at electrolytic capacitors, you see that the capacitance is higher than the MLCCs, and also the voltage is fairly high. But if it comes to film capacitors, you see that the voltage of film capacitors is even higher than electrolytic ones, which gives them several benefits. And also the capacitance is in the medium range here, which gives them some benefits over MLCC, for example. And then for sure we have also supercapacitors, but they are somewhat completely different. So they offer a lot of capacitance, but the voltage is very small. In our case, 2.7 volts. So therefore the voltage is limited. Let's speak a little bit about MLCC. What I showed here is the general structure of an MLCC. You see here the termination layers, and then also here the ceramic body, which can consist of different materials. For class 1, for example, it's titanium oxide, and for class 2, it's based on barium titanate, but always the materials always change a little bit, just some general indication. And what you can see here on the right-hand side is a cross-section of a general purpose MLCC. And you see here there's a big black part, and you can see here that these are the different layers of the capacitor. So they are the distance between these capacitor or these layers is very narrow, so therefore it helps us to achieve high capacitance for these products. If we speak about MLCC, then we always have class 1 and class 2 ceramics, and this is really the biggest biggest difference here. If we speak about class 1 ceramic capacitors, such as NP0, COG, they have a fairly small relative epsilon r, which means that the capacitance is fairly small. But they have no dependencies, or more or less no dependencies, so the capacitance is very stable. They have very small linear temperature dependency, more or less no aging, and also very small voltage dependency, more or less zero. For class 1 ceramics, it's completely different. We have a very high relative permittivity, which leads to a lot of capacitance, but we have strong effects. So we see a strong capacitance drop with applying voltages. We have also an aging effect. So therefore, class 2 ceramics, a lot of capacitors initially, but if I apply some voltage or if we have some aging, the capacitance can drop. So this is the main difference here when we talk about the inner structure. What I showed here on the right-hand side is our MSCC portfolio, and you can see for which voltage and which capacitance we have which ceramic material. So you can see here the class 2 ceramics, for sure, as I mentioned here, class 2 ceramics, a lot of capacitance. So you see because of the high epsilon r, we have the high capacitance values with class 2 ceramics for sure. And the small capacitance values, we have them with class 1 ceramics, but again, the benefit is that they are very stable. So, as I mentioned before, class 2 ceramics, they show some effects, especially when it comes to voltage. What we show here, this is only class 2 ceramics. We show here 4 different parts. These are 1 microfarad parts. So 4 different parts with 50 volts. We just changed one thing. We changed the size of the components. So therefore, if you try to reduce the size of your components or of your system, please take care that the capacitance is sufficient for your design and that you are not facing any problems because of this behavior. So you see that capacitance will drop more if the size of the capacitor will get smaller, because the capacitors, they are more dense, so therefore the effects are more dominant. And we show these values in our RedExpert. We do the measurements for all the parts. You can use RedExpert to check for these parts. Then we have also the aging of MLCCs. Aging, but this is also only about class 2 ceramics. So class 1 ceramics, they don't have any aging. For class 2 ceramics, they have different aging because it really depends which material was used. For example, like X7R has more or less a better aging behavior than X5R, but it also changes from product to product. What happens inside of these components? So basically, when these components leave the production site, they directly start to age because the inner structure will change a little bit. So therefore, the polarization is not so easy anymore, and therefore the capacitance of the capacitors drops over time. And you can see it also here on the left-hand side. This is a drop with a logarithmic scale. So you see that there's some drop, and you can see also that it's a little bit different when we talk about different technologies such as X7R, for example, has more or less a smaller capacitance drop over time than X5R, for example, but they lose capacitance over time. And what can we do in order to restore it? In order to restore it, we need to exceed the Curie temperature, which is 130 degrees more or less. So therefore, one solution could be to use the reflow oven. So for example, if you store these parts maybe a little bit longer, or they were stored somewhere else a little bit longer, after leaving the reflow, they will be restored and the aging, resetted, and the aging will start again. So maybe some conclusion of the capacitance yield of class 2 ceramics. We have here a 22 micron micron part with 10 volts, 1206. And yeah, on the data sheet we write plus minus 20%, which can lead to the negative value of 17.6. And then you have also the temperature dependencies, which is allowed because it's X5R. X5R means that the R means that, or the R stands for 15% capacitance change in the operating temperature range. So therefore you can also lose some more capacitance. And then we applied like 6 volts for these parts for a 10 volt rated part. And we lose a lot of capacitance for this part because it's also, yeah, more or less, it's a very compact and very dense part. So you see we have a strong capacitance loss over DC bias. And then we have also the aging. After 10,000 hours, a little bit more than 1 year, we have an aging effect. But yeah, this is a logarithmic effect. So therefore, for the next year, the drop will be for sure smaller. So you can see that in the base case, you would have maybe 12.5 microfarads. In the worst case, you would have like 6.1 microfarads or something like this. So therefore, you see that you lose a lot of capacitance of your initially planned 22 microfarads. But I have to also to say that we just summarized or added these effects up. But yeah, in reality, so the difference might, or the drop might be not so strong because aging, for example, might be a little bit different if you applied DC bias voltage, for example, before. So therefore, yeah, the value could also be a little bit better. But what can we do, or what can you do in order to select the right part for your application regarding these, yeah, capacitance drops for class 2 ceramics? One good way is to use Red Expert in this case. So I just created an example here. Example, you need maybe 0402 or 0603 or 0805 MSCC with an application voltage of 24 volts. And you want to select the part with the maximum capacitance under these constraints. So therefore, you can use Grid Expert, set the filters, as I mentioned here, also with the rated voltage here. And I showed here the filters and also the rated voltage filter. And then you can see the list which is still remaining. And below of this list, you can also see the DC bias curves. So for example, this one is capacitance versus DC bias. And then if you're logged in, which is completely free, you can move these sliders and also click here and set here your application voltage. And what happens if you do so? There will appear a new column here on the top side, and you can then also filter this selection based on this, based on your operating point, and then you can see what is the best part for my application, so the part with the highest capacitance under these constraints. So therefore, it might be that this part is the best solution for you. But what we can also do, for example, if you use simulation, we also improved our LT spice models because we added now also the DC bias models. For example, if you click on Red Expert here, and here on this folder, you can download the PSpice model, and then you can decide if you want to use the DC bias model or the simple models. If you use the DC bias models, these models will directly take into account the DC bias behavior of these capacitors. So therefore, I think a good solution. Yeah, we have also some safety capacitors for MLCC, which are shown here on the right-hand side. Y2 or X1 capacitors and also X2 capacitors. Especially for the Y2 and X1 capacitors, we have the internal series connection, because if you might have some cracks, for example, this gives the benefit that you won't have a short circuit, which would be very dangerous for especially Y2 capacitors. If we speak about some cracks, because when MLCC fail, and they are not failing very often, but when they do, they usually tend to crack. And this is something what we what we can solve by using soft termination capacitors. These soft termination capacitors, they have a highly conductive polymer material in the termination layer, which gives the benefit that you can bend or that these parts can handle better mechanical movements because they don't crack and they have this polymer material there. So therefore, what we also confirm in the datasheet, for example, the capacitor is soldered here on the bottom of the PCB. The PCB has a length of 10 centimeters. Then it's possible to bend it by 5 millimeters, and the component still needs to fulfill all the specified parameters. So this is something what we also confirm on our datasheets for this soft termination CSST capacitor. So for MLCC, we have these available series. We have general purpose series. We have a mid and high voltage series with up to 3 kV. We have the high frequency series with fairly small capacitance values and also NP0. These are especially used for antenna matching, for example. And then we have also the soft termination capacitors, as I mentioned before. And then we have also the safety capacitors for Y2/X1 application or for the X2 rating. So these are the available series for our MLCC. So let's start with the film capacitors. I also gave here some samples for the film capacitors. You can see them here, the samples of the film capacitors. And if we have a look at the overview, you can see that we have here the metallization on dielectric on the right-hand side, and we have also on the left-hand side the metal film. And you can produce film capacitors with the metal film if you would have them the metal film and then also the plastic film, and then you will wind this up. The benefit is that these parts can handle a lot of current, but there are also some disadvantages, such as the capacitance in the same. The capacitance is fairly small because the metal layer are pretty thick, so therefore you cannot have so much capacitance in the same package. But this is completely different for metallization and dielectric. So for these parts, we will have a dielectric material. And then on top of it, we will have the metallization layer. You can do this also with paper, or use plastic film, which we use. And then we can also decide between polyester and polypropylene, for example. There are also some other materials, but I just want to focus on these parts because we also cover them. So if we speak about polypropylene, these capacitors, these types, they offer a way better dissipation factor than polyester film. So this is a big benefit. And also the capacitance is more stable over temperature for the polypropylene. But polyester, they have also some benefits because generally speaking, this material can withstand higher temperatures. So therefore, you can see also in the market for some high temperature series, some manufacturers use MKT or polyester material. Yeah, let's talk a little bit more about the construction and the safe healing process. You can see that here's the construction. There is the two different layers, so like polypropylene metallization on top, then another layer, polypropylene metallization, a little bit separated, then everything will be wound up and will be filled into this housing or in this plastic box, and then filled up with some with some resin to prevent moisture from creeping inside. But there are also some big benefits for this metallization or for this metallized film capacitors. This is the so-called safe healing process. So just as an example, we have here the dielectric material metallization on both layers, or on this side and this side. And just imagine we have a very small defect, but we apply some voltage. This would lead to very short time short circuit, very local short circuit, which gives us the benefit that the metallization layer is due to this high temperature here locally will be vaporized. So therefore we won't have any short circuit path anymore, and this capacitor has a self-healing, so to say. So this is a big benefit of film capacitors, or of metallized film capacitors. So we have also some AC safety film capacitors, for example X capacitors and Y capacitors. X capacitors, they should be connected between L and N, and Y capacitors, they are connected between L and P or N and P. So yeah, these are different safety classes. We have both of these technologies. You can also separate or differentiate between these classes by checking for the impulse voltage, which was applied after this standard here. So you see that X2 capacitors, they have to withstand 2.5 kV, depending on the capacitance. And for Y2 capacitors, you can see that the impulse voltage is 5 kV. So therefore you see that the safety requirements is way higher for Y2 capacitors. And this is also very important, as you would connect this one here to protected valves. And for sure, it's important that these capacitors won't fail there. Yeah, let's speak a little bit more about X2 capacitors. So generally speaking, there are also like standard X2 capacitors, and there are also like THB X2 capacitors. Standard X2 capacitors, for example, our series FTXX or FTX2, they are cost effective, and they are also sensitive to humidity and temperature, but they offer the benefit that we have them in very small sizes. But the problem for these parts is here. We show it on the right-hand side. So yeah, you can do some tests, such as the 85-85 test over 310 volts AC. And you see that the capacitance drops a lot for the regular X2 capacitors. So therefore, we also added another series. We improved these parts a lot to have a very low moisture absorption. The sizes are a little bit different, a little bit bigger than the other ones, but for a lot of situations you will have the pin-to-pin replacement. These are the THB capacitors. THB stands for temperature, humidity, and bias. So temperature, which will be here 85, humidity 85, and then the bias is 310 volts AC. So this is some information about THB X2 capacitors. If we speak about film capacitors, we also can speak about DC link capacitors, which is our WCAP FTDB DC link series. So these capacitors can be used in a DC link circuit, such as bus link capacitors or bus link capacitors. This series offers 1 microfarad up to 75 microfarads, so more capacitance than other film capacitor series, and they also offer high voltages. They use MKP because it's a very efficient material. We have temperature up to 105 degrees. Something what is very important for these parts, we have the very high ripple current capability of these parts. So our standard portfolio, the part with the maximum ripple current is 25 amps, 25.7 amps for these parts. So you see, if you have like DC link topologies with a lot of ripple current, you can use film capacitors or DC link film capacitors from our side. So then I will give a short overview about the film capacitors. You see here we have the general purpose DC capacitors. We have the DC link film capacitors for this DC link circuit, as I mentioned before. And then we have also the class 2 film capacitors, and then we have also the THB class 2 capacitors, which offer you some benefits when it comes to when we talk about harsh environmental conditions. Then we have also the Y2 capacitors. We recently added them, so we now have also Y2 capacitors with as a film capacitor. Yeah, just to give you a general overview. And now we will talk about aluminum electrolytic capacitor. I also brought some samples here. So you see here the samples for the electrolytic ones. We have bigger capacitors such as the snap-in types. We have the THT ones. We have also the aluminum polymer capacitors, and we have also the aluminum hybrid capacitors. So let's speak a little bit about the inner structure of an aluminum capacitor. You see here, we have here the inner structure, such as we have the aluminum foil, or we have two aluminum foils, and then we have some paper in between. Everything will be wound up, and then will be soaked with some electrolyte. Will be then closed with sealed with the rubber seal here, and the aluminum can, to prevent that these capacitors can dry out. But they are not only the typical aluminum electrolytic capacitors, which you can see here. So left-hand side anode material, right-hand side cathode. We can also see this black layer, which is the oxide here in between. Then we have some electrolyte here in the middle. The problem is here for these parts that this electrolyte can dry out, so therefore the surface would increase, and also ESR will increase. The surface will decrease and ESR will increase, so gives us a lot of benefits and also limited lifespan. But the benefit is that we can produce these parts in different shapes. We can produce them very small, we can produce them in medium size, and even in big size, because we can do this based on our production capabilities. But there is some disadvantage of this part. And what we can do is to use aluminum polymer capacitors. Aluminum polymer capacitors, they have a highly conductive polymer material here in between, which cannot dry out, and it's also highly conductive, more conductive than the electrolyte material, which gives us the benefit that we can apply higher ripple current for these parts. But we are somewhat limited when we talk about the sizes, like SMT or THT. And there's also some other disadvantage, what you can see here. So just imagine if you would have some small defect in the oxide layer due to some mechanical vibrations, movements, whatever. For electrolytic ones, it's no problem. These layers can repair itself. If you apply voltage in your application, you will have the anodic oxidization again, and this oxide layer will repair itself. But for polymer capacitors, it's not possible in this way, because you don't have the oxygen to repair the oxide layer there. So therefore, the leakage current is specified higher for polymer capacitors. But what can we do? We can add again some electrolyte. So just a little bit of electrolyte. These are the hybrid polymer capacitors, where we produce a polymer capacitor and then add a little bit of electrolyte to have again this benefit of the limited leakage current and of the self-healing behavior there. But also here the sizes are a little bit limited. When we have a comparison of these three technologies, you can see here I selected three 100 microfarad, 16 volt, same size capacitors, electrolytic, hybrid, and polymer. You can see that the ESR of the polymer is by far the smallest in comparison to the electrolytic ones. But the hybrid is like not in the middle, it's very close to a polymer capacitor, because it's more a polymer capacitor than an electrolytic capacitor in this case. You can also see that the ripple current is way higher for the polymer capacitors and hybrid ones in comparison to electrolytics. And you can see here the big benefit of the hybrid ones. You can see here that the leakage current is way smaller than the polymer capacitor. So this is really the big benefit of the hybrid capacitor. What we can also see is here when we speak about the endurance, the hybrid capacitors, or this part is specified for 10,000 hours at 105 degrees, so especially interesting for high temperature designs. And if we do the lifetime calculation, you see at 65 degrees, the lifetime of electrolytic ones would be a little bit more than 3 years. For the hybrid and polymer, it would be 13 years max. Why is it 13 years max for the polymer? Because we use a different calculation formula, which means if you go 20 degrees below the maximum rated temperature, you will get tenfold of the original or initial specified lifetime. So therefore, you will get way more lifetime when it comes to smaller or to lower temperatures. Just some overview, what series do we have? We have, for electrolytic ones, we have radial THT, V-chip SMT, snap-in capacitors or screw capacitors, so we can produce a big variety of capacitors, also very big ones. For aluminum polymer capacitors, we are a little bit limited when we talk about the size. We have THT and SMT parts, and we have also the H-chip SMT aluminum polymer capacitor, which gives us a benefit. For example, if you have a very small or if you have a design where you have where you have to think about the height a lot, so therefore you can use the H-chip aluminum polymer capacitor, but the voltage is limited. So yeah, it really depends on the application. Then we have also the aluminum hybrid polymer capacitors. These are also limited in the size. We have 4 different series here. You can see here the different specs. Yeah, this is the overview for these parts. Let's speak a little bit about the DC-link application. So, for example, if we want to select a DC-link capacitor, we can either use film capacitors if we have high ripple current requirements, or if we don't need so much capacitance. We can also use electrolytic capacitors for sure, because for these parts, yeah, they offer a lot of capacitance, but the voltage is a little bit limited. Also for some applications, you can also use MLCC or combine them even with electrolytic ones, for example. So you can see that also for some applications they can be used, but the capacitance is very small, so therefore the applications they are limited. Here's some general technical comparison of film capacitors and electrolytic capacitors in the DC-link technologies. For the film capacitors, we have a lot of ripple current per microfarad. We have high rated voltages, so no need to connect them in series. We have no liquid, self-healing properties. We have it also because it's metallized film capacitor. And if we speak about electrolytic ones, we have the highest capacitance per volume and also the highest capacitance per dollar in this case. But the disadvantage is that we have a relatively high ESR, which leads to an increase of temperature inside, and therefore also limits the ripple current capability of these parts. And also some other disadvantage is the rated voltage of 650 volts maximum here. So therefore, if you have higher voltages, you need to connect them in series, which gives you some benefits, some disadvantages for sure. So let's speak a little bit about hybrid polymer in the DC-link application. I directly put here some question marks because there are some things to consider. We have the DC-link requirements of high ripple current, we have the low ESR, we have the size, we have the high reliability and lifetime. For the RMS current, we see here that also these hybrid polymer parts, they have a very low ESR in comparison to electrolytic ones, so this gives us a lot of benefits. Yeah, we have also low ESR to limit the self-heating, which is more or less the same. We have also some size requirements for some applications. So hybrid polymer capacitors, they very often offer a very a solution with a low height, so therefore you can realize dense inverter layouts. And also when we speak about the high reliability, you can see we have added here the electrolytic, which gives us some benefits over polymer capacitor, and it supports the oxide regeneration. Then I also compared here electrolytic, aluminum electrolytic, hybrid polymer and film capacitors. For sure, if we start with the electrolytic ones, they have very low cost. The capacitance is high. They offer higher voltages than hybrid and polymer. And if we speak about hybrid polymer, they offer low ESR, high ripple current capability. Yeah, they are very compact and they have also a good thermal performance. But the disadvantage for hybrid polymer is that the sizes are limited, same like for polymer. And therefore we have also a limited voltage. And from our side, it's maximum 100 volts at the moment. So therefore these applications are limited a lot because the voltage is only 100 volts there. If we speak about film capacitors, they offer very low ESR, excellent ripple current capability, long life, and also what I didn't write here is that the voltage for these film capacitors is very high, so you don't need to connect them in series. But the disadvantage is you don't get a lot of capacitance in the same package. So just to compare the different technologies for the DC-link application. Just a short summary of today's webinar. We started with MLCCs. These offer the smallest size. They have also high voltages. For MLCC, we always have to speak about class 1 and class 2 ceramics. Class 1 ceramic means very small capacitance value, but very stable. Class 2 ceramic means high capacitance value, but very unstable, a lot of DC bias and so on. We have also the safety capacitors here, such as Y2 capacitors, for example, or X2 capacitors. And to limit possible cracking, use soft termination. If we speak about film capacitors, they are suitable for high voltages. No need to connect them in series for high voltages. We have the self-healing properties. We have safety capacitors available, X2 capacitors or Y2 capacitors, which we recently added. And we have also the THP capacitors, which can be used if you have high humidity and high temperatures for your applications. And then we have also the aluminum polymer, aluminum capacitors. For example, electrolytic capacitors, very cost efficient, big variety in size. Then we have also the polymer capacitors. They are suited for longevity applications with low ESR values, but they are not suited for battery powered applications because the leakage current of these parts is fairly high, so therefore not recommended for this application. Then we have the hybrid polymer capacitors. They combine the advantages of both technologies because they have also this electrolyte, which gives us the benefit that the leakage current is limited for these parts. They are also suited for longevity applications because they are especially specified with a long lifetime at high temperatures, which is also shown here. So thank you so much for listening, and I'm now happy to answer the questions. Thank you.
Yeah, thank you, Lukas, for your interesting presentation. Now we will come to your questions. Before we start with the Q&A session, I will share the handout from the presentation today. And now you can download it. Now the download is ready. So then we will start with the first question. Question about slide 5. Why does ESR reduce with frequency? Should it not increase due to skin effect, etc.? It's a question about slide 5. Yeah.
It's maybe this one. Yeah. So maybe for this question we can check it later on. We can also do maybe a short seminar about this and to speak a little bit more about these different behaviors here.
Then Next question. In which group shall be polymer capacitor?
Maybe if we speak about this one. So I don't know if this was the question, but we can see that the polymer capacitor, they will be here in the electrolytic capacitor section, because they, you know, the structure is we use aluminum here, and we have the aluminum oxide, which is the main factor to describe how much capacitance we can have in this package. So therefore, it's yeah, here.
Mm-hmm. Then next question. This one. Why is the ESR frequency dependent?
Yeah, I think it's more or less same question like before. The ESR is for sure frequency dependent. There are also some effects like skin effect and so on, but I think it's better to to discuss it later on.
The next question, can you compare the different types of capacitors in terms of reliability?
I mean, yeah, it really depends which capacitors you want to compare. For example, if you compare the classic X2 capacitors with THB capacitors, you can see that the THB capacitors, they are way more reliable because the capacitance does not drop so much with temperature and humidity. But generally speaking, yeah, it's really difficult to say something about each technology, because we really need to check, okay, which technology we need to compare. If we now can speak more about electrolytic fonts and polymer capacitors, then we can go more into detail. But I think this is also something what can be checked afterwards. But generally speaking, for example, if we speak about the electrolytic and the polymer ones, electrolytic ones, they offer the benefit of the self-healing, so the oxide layer can be repaired. And also the hybrid capacitors, they have this behavior. So if you have some vibration, for example, then polymer might not be the best solution. But it really depends on the application. It's not so easy to give a general statement here.
Mm-hmm. Then next question. You mentioned the problems of tantalum capacitors and flammability, but this problems is mainly in main Q2.
Yeah, so I understand. So the question is that this. Yeah, so the question was that this problem of flammability is not is for polymer tantalum. They don't have this problem, and the question was also if Würth have such polymer tantalum capacitors. So we don't have them, and at the moment we also don't plan to have them, because we had especially for the smaller voltage and tantalum size D, we had the H-chip polymer capacitors. So yeah, we will not go into the tantalum capacitors, also because, you know, the prices are also a lot of changing a lot for tantalum capacitors, and yeah, generally it's at the moment it's not a technology that we want to support at the moment.
Thank you. The next question. Can you tell also something about the X2 capacitors?
I'm not sure if it's about X2 capacitors or if it's also about Y2 capacitors. So I think we can also discuss it maybe later on. But yeah, X2 capacitors, they are usually used to connect between L and N, and for Y capacitors we have this internal series connection. Maybe we can also speak about this this afterwards. Maybe.
Okay, then I would say one last
maybe one
question.
More,
yeah. this one. Why are supercapacitors limited to very low voltage, despite offering capacitance up to 1 kF?
Yeah, thank you. It's a good question. I mean, we try to increase the voltage for these parts for sure, but so the reason is that the inner structure or the electrolyte will be destroyed if the voltage will be increased. So you can see also in the market maybe like 3 or 3.3 volts, but this is more or less the limit. What you can see sometimes that you have the 5-volt parts, but then usually they are connected, 2 of them in series. So yeah, the voltage is really the limitation there. And then if you connect 2 of them in series, you need to make sure that you are doing the balancing properly. So either resistive balancing or there are different options. So if you need to connect them in series, please contact us, and we can help also here.
Okay, thank you. Then I would say this is the end of the webinar from today. Thanks for joining. Thank you, Lukas, for your time and for your presentation. Hopefully we see us on our next webinar. Have a nice day and bye-bye.